Welcome to the video lecture series for HEAL 518. We're going to cover what are inferential statistics. And this particular lecture series scares some students, and I just want to put out there up front that it scares me too sometimes, because when I first started learning statistics, I was a little bit stunned by all the math you had to do in understanding this. So that's fine, but this video is going to just get you acquainted with some of the basic concepts. And so later on we'll get into the how to actually calculate some of these statistics. So get familiar with the words and the lingo and the concepts, and we'll get more comfortable as we go forward. What we're going to cover today are the basics of inferential statistics. So we're going to talk about what it means to estimate using a sample versus the total population. So what does that look like? The types of inferences we can make, hypothesis testing, and then we're going to talk about statistical significance parameters and confidence intervals. What are those things? So a lot of fancy words we're using. Then we're going to talk about calculating inferential statistics. So how do we choose the right tests right off the bat? So what are some of the things that we can do to make those decisions? How do we know which test to use and which test statistic that we're going to need to calculate to understand the statistical significance of our data? And I want to take you through some of the common tests that are used when you have a certain set of data. And we'll just cover some of the basic ones. In the next lecture, we'll talk about correlation and regression, which are two types of inferential statistics that kind of take you to that next step and also take you to causality. So when we're looking at regression, we're thinking about causality. All right, so let's get going with the basics. So if we think about generating scientific knowledge and why we go through all of the struggle to collect information to kind of assess the world, we look at populations in public health, and we collect information about populations because it really is real expensive to collect information from an entire population or to do a census. In the United States, we conduct a census every 10 years. Because it's incredibly expensive, and we really only conduct the census for governmental purposes. We don't do it for health or humanitarian purposes. So in health research, we do a process called sampling, or we take a sample from the population and collect information about that sample and create a data set. That data set, then we can describe that data and conduct descriptive statistics. From that set of statistics, we can then make inferences. We can conduct what we call inferential analysis. And we can also do significance testing. And then it gets really murky and fancy where we can estimate parameters, or what I call characteristics about that population based on that sample. This is a giant cycle. All right, that sounds like a lot. Let's break it down a little bit more. All right, so in the previous lecture, we talked about descriptive statistics and how you can kind of work from taking that sample and describing it. So once you've described that, let's look at this sort of relationship between the sample and the population a little bit more. So we collect a sample using a data collection method of our choosing based on our study design from that population of interest. So your population of interest could be school children. And we want to just take a subset of, for example, all children from a specific high school. So we're going to take just a sample of high school children. And we're going to take that sample and use that sample to make predictions or draw conclusions about our population. And that is inferential statistics. We are going to make inferences. We're going to make predictions. We're going to draw conclusions. Now, some of my students use the word guesses to describe inferential statistics, and that's really not the greatest word to use because it's not a guess. It's an informed guess. And so I encourage you to say inference or to draw a conclusion that is based on evidence. A prediction is based on evidence. Is what we are seeing in our sample real? And how confident are we that it is real, that it represents what's going on in the population? Because again, it's cost prohibitive, too time intensive to collect information from everyone in the population. So this concept of using the sample to represent what's going on in the population and to make inferences, to predict things about the population based on that sample, that's what inferential statistics is about. And so what kind of inferences can we make based on that sample? There are two basic inferences you can draw. The first is to look at relationships between variables. So if you look at your data set, you have those columns, and those are representing variables. For example, height, weight, blood pressure, the HbA1c. You might also have categorical variables like male, female. You could have a column for gender identity. You could have a column for your disability status. There's lots of things you could collect. Okay, so you might want to understand relationships between variables within your data set and to examine those very specific relationships. Are things related to one another? Does one inform the other? What happens to one when you change the other? So for example, sleep and obesity, is there a relationship between them? Does not getting enough fluoride relate to the number of dental caries that children have? Or does the number of hours you exercise relate to body weight? And if so, in what direction and how, what is that relationship? And so sometimes you can look at that in your descriptive data. You can see a real difference in, for example, the relative frequency, the proportion across these variables. Okay, but are these relationships real? You can test that with inferential statistics. So that's one category. The second category we can look at are differences between two or more groups, but let's just focus on two groups for the moment. So this is often where we get into experiments, when we conduct studies where we examined one group versus another group, and we examine whether or not differences in one outcome exist, and are they real? Are those differences real? For example, does protection from COVID-19 across groups of people with different doses of vaccine, so if you have like 3, from none to 3, so there's different dose levels you can get, does that change? Do you have different levels of protection? And is that statistically different across those groups? So ranging from a group that has no vaccine to groups that have have received all 3 boosters. Okay, great. So you can actually look at that. What about the number of injuries sustained by high school athletes in schools that are following concussion protocols versus schools that are following older protocols that don't have concussion protocols? So you've got 2 different groups. And note, in that second example, I'm using institutions, schools, as my unit of analysis. So it doesn't have to be people. We can make inferences about other kinds of units, not just people. We can look at schools, organizations, we can look at states, different kinds of entities, and look at the differences. But it all comes back to the question, is this real? And to get at how real something is, we have to make some kinds of informed guesses. Informed, again, I'm using that word guesses, but it's informed. We need to make estimates. And we can do that using inferential statistics. But I want to also explain that when we do that, we have to have a research basis for this. And the important part of this process in research is to have a good research question and to really think about, why am I asking what I'm asking? If I collected data, I had to have had a reason for it. And oftentimes it starts with a hypothesis. So we make predictions about the population that we're interested in, and these are called hypotheses. And we can test these using statistical methods in inferential statistics. There are 2 types of hypotheses that you probably are familiar with, but let's just re-familiarize ourselves with these terms. And the first is the null hypothesis, or H0, that states there is no difference between that sample parameter and the population parameter. And the word parameter, to me, I'm just saying characteristic. So the sample characteristic and the population characteristic. For example, the percentage of dental caries in one in the total population versus in the sample population. The alternative hypothesis makes an opposing prediction to the null. It says, no, it's not going to be that there's no difference. It's going to be an actual difference. And I'm going to make a prediction about what that difference actually is. So they quantify what that difference might be. And so you collect data from a sample. You conduct statistical tests to confirm or reject that null hypothesis. But we always go with the assumption that the null hypothesis stands. So it's sort of like this innocent before guilty concept in a courtroom, that we're just going to assume that there's no relationship. No one did anything. That the data are what they are. There's no difference. We're not going to see any difference. But if we do see it, it's because of something that didn't occur by chance. So we have to think about our predictions, and again, our predictions are informed by our observations in the natural world and looking at the literature and understanding the scientific basis of our hypothesis. So there has to be some kind of evidence before we make a prediction. And so we have these two hypotheses. We can now look at an example to apply these two concepts. So, for example, in generating some clinical evidence, we might want to conduct a randomized clinical trial. And in a randomized trial, for example, in this case, blood pressure medicine is being tested. We want to examine a group of 200 people. In a randomized trial, what we do is you recruit a group of people, and you say, we're going to give you a drug, and you do not get to choose which drug you get. You're randomly allocated. So you get to say, sign up for the drug, and you either get the drug or the placebo randomly. And so that's randomly assigned to you. And the great benefit of being randomly assigned is that you reduce the likelihood of chance ruining your experiment or biasing your experiment. You kind of create that sort of artificial kind of balance at the beginning. It's not artificial, it's random allocation. And so you have treatment and control. Assume you have 100 in each group. And the treatment group gets the drug and the control group gets a placebo. And assume it's blinded, so they don't know which one they're getting. And my outcome measure, or my dependent measure here, is systolic blood pressure. And I'm going to measure that after 1 month. So I'm going to measure it before and after 1 month participation. And I notice there's a reduction of 12 points versus 5 points. So 12 points reduction in the treatment group, 5 points in the control group. And my p-value, which I'll get to in a moment, is 0.01. Interesting. We'll talk about what that means in a second. But you'll note that there is more of a reduction in the treatment than in the control group. So that sort of tells me on its face that the blood pressure medicine seems to work. My hypothesis in the beginning was that this drug will result in a significant reduction of blood pressure in the treatment group compared to the placebo. So it's important to get into the habit of actually stating what your hypothesis is. My null hypothesis, again, is there's no difference. So there will be no significant difference in blood pressure between the two groups. And if we do see any difference, it'll be due to chance. So it's important, again, to write these hypotheses out. No matter what you're testing in inferential statistics, write out these two hypotheses before you start. All right, so remember that p-value there. So let's back up and look at some of the terms I've used. So we have a treatment and control, we have systolic blood pressure, and we have a time, and we have a drug that's being used to control blood pressure that's experimental. So in this case, our dependent variable is our outcome. That's systolic blood pressure. The thing we're trying to change is always the thing that is dependent on something else. So that is systolic blood pressure. We're trying to shift what happens to blood pressure. And our independent variable is the thing that's we're manipulating. Whatever we can independently manipulate is the independent variable, and that's our experimental drug or treatment. Anything that's in between, anything that intervenes that could explain causality or could actually shift the relationship between these two variables, either that it's related to the dependent variable or it is related to the independent variable, or both, is it called an intervening variable. So things like age, exercise, or other medication. These are important labels that you'll hear in inferential statistics and understanding how to interpret some of this literature. So be aware of these terms and how to identify them in the literature and how to use them when you talk about statistics. So what is statistical significance? You'll note I talked about p-value a few moments ago. Statistical significance is the likelihood or probability of a given set of results being obtained if the null hypothesis were true. That's a lot to take in. So we usually allow about a 5% chance, or 0.05, in social science. That just means that there is less than 5% chance our null hypothesis is true. This is also called type 1 error. So this is our chance of being wrong in rejecting the null. It's also called the alpha value. This is our alpha value. And so this cutoff, by the way, this 5% level is completely arbitrary. Somebody at some point decided that this was okay, but this could have been set somewhere else. But 5% is generally where people see it. And so you'll see p-values, or probably of 0.05, being the cutoff that we use to say, all right, that's when we're going to say that, that's our cutoff for rejecting the null. Okay, that's fine. So in our blood pressure trial, you'll note that we had a p-value of 0.01, or 1%. So there is a 1% or lower likelihood that the bigger reduction in systolic blood pressure is due to luck or factors other than the experimental drug. So when you see a p-value and are interpreting statistical significance, that's all that really means. That's that alpha value, that statistical significance or cutoff. And again, that 5% is arbitrary. It's been chosen by other people before us. In fact, I don't actually know who has chosen that value. I'm sure my own professors who have taken these courses from would not know who that is. It might be Fisher, it might be Pearson, I have no idea. But that's the cutoff that we typically use in most of the social sciences and beyond. So be aware of that cutoff. I've also used words like parameters and confidence intervals, and I just wanted to cover those concepts briefly so that when you are reading papers, you can feel confident about using those. So parameter, again, is just a fancy word for the characteristics of your sample. So if I'm estimating a parameter, it just means the characteristics. So in this table, you'll see body mass, HFL, white blood cell, WBC, monocytes, the different components of the blood that is being described for the sample that is being divided by sex assigned at birth, males and females. You'll note that the mean value by parameter / characteristic is being presented here in this table. But there's also a confidence interval being presented in this table as well. And this is just a range of values that is likely to include a population value with a certain degree of confidence. So that just means how well does our sample represent the population? And that's usually 95%. So does that value fit in with that 95% range? And so when you see that mean value next to those columns where you see the 95% calculated CI, does that mean fall within that range? So if you look at, for example, the mean value for males, 16.9 for body mass body mass kilograms, it falls within the 95% CI. And so that just means that that value is within the population value there. So we can feel that our sample does in fact represent that population well. So that increases our confidence. And so you'll look at this data and feel like you can say confidently that the data that you have in your sample is significant. And so you can also look at the confidence interval, and if your parameter, your estimate is not contained within the confidence interval, you can also say that it does not meet the cutoff for your alpha level to begin with. You don't even need the p-value to know that it's there. So just be aware of these terms. All right. Final word before we shift to some of the tests that you'll use for inferential statistics. Sampling. So when moving from your population to your sample, you've taken a sample. Sampling is really important. Sampling is just the process of taking your sample through data collection. Whether you do a survey, you recruit people to participate and provide clinical data such as blood pressure or blood samples. To make a good inference, your sample needs to accurately represent your population. And so the quality of your inference that you make from that sample is affected by three very important things. First, how much sample you have. A sample of 1 is anecdotal. So for example, you'll note that out in the world, people will say, well, my experience was this, and therefore everyone should listen to me because my opinion is incredibly important and therefore represents everyone out in the world. And we know that is completely wrong, that an N of 1 doesn't necessarily mean that we should make inferences about that one person's experience and extrapolate that to an entire population. But if we have more sample and we've collected that sample too in an appropriate sampling method, such as a probability-based approach like random sampling, or that we have collected that data, and we have collected that sample systematically without error. So we have done it the same way for every single person. We've collected the survey in the same way, and they've answered the same questions using the same methods. Then we can increase the quality of our data, and therefore the quality of our inference is improved. So having more data matters, but sometimes you can reach a limit to how much data you actually need. And so there are entire courses based on how much sample you need, which increases something called statistical power. So you can get to a magical number that tells you how much sample you need in order to have sufficient power to detect differences between groups or between variables. And this is an important concept that is something to consider when you interpret inferential statistics. Now, moving on to calculating inferential statistics, let's first talk about choosing the right tests. So there are three things to consider here. What type of data do I have? How is my data distributed? And what are my research questions? Or do I even have one? So first, what type of data do you have? The kind of test that you do defaults primarily to the kind of data that you have. If you have, for example, numerical data, you're not going to conduct a test that is designed for categorical data and vice versa. So, for example, nominal data is almost always entirely categorical. And so you'll want to look at your level and type of data and use the right test designed for that kind of data. And you'll also want to look at how your data is distributed, the shape of your data. So, for example, we have different kinds of distributions, like the normal bell curve that you're used to seeing, like on the graph on the left here, as a parametric distribution. But not all data is parametric, and some data is non-parametric. So you will want to use the right kind of test, and you might need to use special statistical tests depending on what kind of shape your data have and the behavior of that data. And so, be aware of how your data is distributed. This is why we graph our data and we use histograms, for example. And then finally, what is my research question? It's important to have one, even if you think that it's not a real research question. For example, what is the height of my entire population compared to the national average height? Well, it doesn't sound like a very interesting research question, but it might be if you're trying to understand whether or not your sample is representative of a national data set or the national census. So here you're asking, am I examining differences in variables versus groups? I'm defining my hypothesis so that I can come up with a right test. So the first kind of test is the one sample proportion test. And here we have one categorical variable. We're going to be estimating the proportion of a population by comparing it with a target or a reference value. So this often happens in epidemiology where you have a population and you have, for example, a proportion of students who have a who have a specific prevalence or incidence of obesity, and you want to compare that to the national rate or the national prevalence or incidence. And so you can do that if you have a reference or a target. The test statistic for this is the Z statistic, and this is the formula for it, which you can calculate manually, and you can calculate any one of these tests manually using Excel or Google Sheets, and you can also use statistical software for it. The chi-squared test is used when you have two or more categorical variables that are non-parametric. This is when you estimate the difference between expected and observed frequencies in one or more categories. And the statistic for this is, again, the chi-square. The test statistic for this, again, you have to have observed frequencies and expected frequencies, and you sum them. There are different versions of this depending on the behavior of your data, and so as you look at your data, you can use different versions of the chi-square. For example, the most common is Pearson's chi-square, and that's probably the one you'll most likely use, but you might also use one that uses, you might use the binomial approach to the chi-square based on a binomial distribution of data. And if you have a very small sample size, fewer, for example, than 20 cases, you might use the Fisher's exact test. And again, it depends on what kind of data you have and a contingency table setup that you have. The t-test is probably the most common inferential statistic that people start out with, and this typically has one numerical variable, though you can have more than one. We're going to compare the means of two groups to see if they're statistically different in this case. And the test statistic here is the t. So the larger the score, the more different the groups are, and the formula is pretty straightforward. There are actually three different versions of this test statistic, but the one that I calculate the most, the two that I calculate the most often in health promotion work are independent t-tests and the paired t-tests. So in the independent t-tests, I'm looking at means for two distinct groups. So for example, treatment versus control in a randomized or quasi-experimental designed study. And the paired t-test to look at the same group at different time points. So if I'm looking, for example, at a survey that I've conducted at different time points and I want to examine differences in, for example, sleep score, I would like to do a paired t-test to look at that mean score over time and look at the difference statistically in those two scores. And then we have analysis of variance, or the Anova. Now, our data here is when we have categorical and one numerical variable. So we're going to assess whether there are statistically significant differences between means of three or more independent groups. And again, here you can also, very much like the t-test, there's a little bit of weirdness here because you can do, it's very similar, but the difference here is that you have more than two groups. I'm showing this test statistic of F for the one-way ANOVA, but there's actually two different ones you can do. There's a one-way and a two-way ANOVA. And you can also do ones where you have multiple dependent variables, for example, the MANOVA. And there's different versions of that depending on how many covariates you have, like the MANCOVA, etc. So depending on how many dependent or independent variables, covariates you have, there are different versions of ANOVAs that you can do. And again, this particular statistic you can run in Google Sheets and Excel, but it's easier to run if you have a statistical package like SAS or SPSS or R or Stata. In our next lecture, we're going to cover two other important inferential statistics, correlation and regression. Correlation, which uses the R coefficient to interpret its estimates, and regression, which is represented by this equation. Regression is where we start getting into causality. So each of these deserve more attention about what they are and how to calculate them and how to interpret them. So as we get into inferential statistics, become comfortable with the language in terms of calculating them. The only way to feel comfortable calculating them is to actually get into doing that. And that's what we're going to do next in our classes. So thanks for listening.